Welcome to my channel. Firstly, I will give a brief introduction about myself. I am Sudhanshu Arya, currently studying in BIT Bangalore, CSE in 3rd sem. This video is about the project given to me by Maya ma'am, our ADE teacher. My topic is counter design using T flip-flop. So let's move to the presentation. First of all, welcome all of you. Now we will see what is a counter. A counter is a device which stores the number of times a particular event or process has occurred, often in a relationship to a clock signal. Counters are used in digital electronics for counting purpose. They can count a specific event happening in the circuit. So basically, they are used for counting purpose in circuits. Now let's move to the next slide. Mm, There are two types of counters. The first one is asynchronous counter and the second one is synchronous counter. Now we will know about asynchronous counter. Asynchronous counter, it is also known as ripple counter. In asynchronous counter, we don't use universal clock. Only first flip-flop is driven by main clock and the clock input of rest of the following flip-flop is driven by the output of previous flip-flops. What does this mean? Let us understand this by diagram. Here you can see in the diagram, this is the first flip-flop, this is the second flip-flop, and this is the third flip-flop. Here we can see in the first flip-flop, the clock input is driven by the main clock, and here in the second flip-flop, we can see that the clock input of the second flip-flop is driven by the output of its previous flip-flop, which is Q0 bar. And here in the third flip-flop you can see the output of the input of the third clock is driven by the output of the second flip-flop, which is Q1 bar. We can see in the diagram that input of the first flip-flop is driven by main clock and the other flip-flops are driven by output of previous flip-flops, which is Q0 bar and Q1 bar. Now we will know about synchronous counter. Synchronous counter has one global clock which drives each flip-flop, so output changes in parallel. The one advantage of synchronous counter over asynchronous counter is it can operate on higher frequency than asynchronous counter, as it does not have cumulative delay because of the same clock is given to each flip-flop. What does this mean? This means that as we know that in asynchronous counter, in asynchronous counter, uh, in asynchronous counter, the the input clocks of the second and third flip-flop is driven by the output of first flip-flop, which which causes a delay, which gives advantage to synchronous counter. Here we can see in the diagram that there are four flip-flops in this diagram, and all the clock input of this diagram is driven by a main clock. This one here, all the clock input is connected to main clock, and this is all connected in parallel. Now we will know about flip-flops. What is flip-flop? Flip Flip-flop is a circuit that maintains a state until directed by input to change the state. This means that it will maintain its state as long as it is not directed by input to change its state. There are four types of flip-flops: RS flip-flop, JK flip-flop, D flip-flop, and T flip-flop. So in our topic, we will study about T flip-flop, which is also known as toggle flip-flop. T flip-flop. T flip-flop, a clocked flip-flop whose output toggles, that is changes to the complementary logic state on every active transition of the clock signal. Here is the circuit of T flip-flop. Here we can see it is T state, and here is the output, and here it is clock. Let us suppose our toggle is 0. Here let us suppose our T is 0. So here is our NAND gate. So this will become NAND gate, and since our toggle is 0, so this will become 1. This will become 1. Now let us suppose our previous state Q is 0. Then and here this will also become 1, and we have assumed that our Q is 0. So here it will become Q bar dash will become 1, and here this one was 1, this one is also 1, so the output of NAND gate is 0. So here we can see that the next state output doesn't change, it remains to 0 as we have assumed. And here we can also see that the next state's output does not change, and it is the same as we have assumed. So when the toggle state is 0, it does not change, and when the toggle state is 1, it toggles its output. So here we can see in the truth table that when toggle state is 0, it does not change. See, here we can see it is 0, and the present state is 0, and the next state is also 0. And when toggle is 0, the present state is 1, so the next state is also 1. But here we can see that when toggle state is 1, the present state is 0, and the next state is 1, uh, which means that it toggles its output. And here we can also see that when toggle state is 1 and present state is 1, so the next state will become 0. Using this truth table, we'll design a counter design. Here we can see that 0 1 3 4 5 7 0. We will design a counter. Here and the state transition diagram is given. See here 0 1 3 4 5 7. This means that when the present state, the next state for 0 is 1, the next state for 1 is 3, and the next state for 3 is 4, and so on. And what about the numbers which is not here? That will go into don't care condition. So here we can see that 2 is not here, 6 is not here, so they will go to don't care condition. See here we can see that the present state 0, the next state is 1, present state 1, the next state is 3, present state 3, next state 4, and so on. Here it is written in binary code. See, and the present these Q3, Q2, Q1 are present states, and these Q3 T plus 1, Q2 T plus 1, and Q1 T plus 1 are its next state. So here we can see that when Q3, Q2, Q1 are 0, 0, 0, then its next state is Here we can see it's 1, so here it is 0 0 1. Here present state is 0 0 1. So for 1 the next state is 3. So here we can see the next state is 0 1 1, and so on. Now we know that when toggle state is 0, then it remains it in its previous state. So for we can see here Q3 is 0, Q3 next state is 0. So here no state is changes. So here we can see T3 is 0, means when third toggle is 0, they will not change. Here we can see Q2 0, Q2 next state is also 0, so T2 will also be 0. Here we can see, and here we can see Q1 is 0 and next state is 1. So here there is a toggle between its state, so the T1 will become 1, and so on like this. T3, the input table of flip-flops have been made. Now using K-map, we will find the equation of T3, T2 and T1. So here we can see the truth table of T3, which is 0 0, so 0 0 1 0 0 1. So here we will using K-map. Here we can see we will consider this quadruple. We will consider this quadruple. So T3 is equal to Q2, and same like that here we will use this quadruple. So T2 will become Q1, and here we will use this quadruple using K-map. So T1 will become Q2. Now we will draw this circuit for the counter. So here is the circuit of the counter. See, here you can see the toggle input of T3 is the output of Q2, and like that we have made a counter. Now we will move to the practical example of a counter. Practical example: in microwave ovens we set some temperature to heat the food item kept in it. Internally the counter What happens there? Internally the counter calculates the increase or decrease in temperature and time. If it reaches the preset temperature, then it prevents from further heating. Also we use washing machines in our home. We use counters there. The counter in washing machine counts the time which we set it to operate. In both microwave oven and washing machine, we set the device to particular time and it starts decreasing for every second. When the value of counter becomes 0, it becomes the switch on or off according to the situation. Thus the operation device is controlled by counters. Here we will see applications of counters. Counters are used in frequency counters. Counters are used in digital clocks, analog to digital converters, calculating time in timers. We can design triangular wave generator by using counters. So that's all for my topic. At last I want to say thank you to all of you for watching this video.